So yesterday we were looking at a Millikan type setup where the oil droplets, the charges, the objects, whatever you have, are balanced, okay? Now obviously you have to get the electric field strength perfectly balanced with gravity for it to be balanced, and there are going to be times when the oil droplets are going to be accelerating, either upwards or downwards. You need to be able to mathematically deal with that. So that's sort of the topic of the day. Okay? So, Millikan had charges suspended between electric plates. Why did he have them between plates? It was because, why? The forces were balanced. And we've drawn this diagram a few times where the electric force was equal to the weight force. But of course, the question is, what would happen if the weight force was, say, greater than the electric force? It would accelerate down. Would it accelerate down at minus 9.8?
No.
No, it would not. Now remember, these are also very tiny oil droplets, and so air resistance has to come into play as well. He had to deal with that. Fortunately, you don't have to. I've simplified things for you. So, you're welcome. If the forces are not balanced, there will be a net force on the charge causing an acceleration. Okay, and that's, again, because you've got a situation, maybe you've got a larger electric force than a weight force, right? And so there is a net force that is, in this case, up, right? Is this any different than if I turn everything sideways and talk about an applied force and a friction force?
No.
It's really one and the same. It's just the vertical version of it, is it not? Okay, so in that sense, it's nothing new. In obviously other senses, it is certainly something new. Okay, so using this net force and acceleration, we can solve problems for motion in the electric field. All right, so now before we get into that, consider a line of charge and a single point charge placed nearby. I'm going to draw you a picture right away. The horizontal components of corresponding charges cancel, and the vertical components add. And you're looking at me going like, what is he talking about, right? Exactly. So what I'm saying is, if you've got a charged plate like so, right, and you've got all positive there, and I've got a positive here, well, this positive charge actually pushes it that way, but this positive charge actually pushes it this way. And so the horizontal components, which I'm drawing here in red, do what? They cancel each other out, right? So what I'm saying is, those of you that may have actually thought about that can stop worrying about that. Those of you that didn't have any idea about that, you can go right on not having any idea about it because it doesn't really matter. Does that make sense? Okay? We don't need to worry about the horizontal component. And in the same manner, this one here, this horizontal component of this guy, and the horizontal component of this guy also cancel out. You need to remember that if there's plates, then the electric field is uniform, right? Okay. If the plates are oppositely charged, the effect is enhanced. I think I'm missing this stuff. If the plates are oppositely charged, this effect is enhanced, and basically the field direction is completely pointed down in one direction, from positive to negative. Is there a little bit of leakage and curvature on the sides? Yes. Do we worry about that? No. For the vast majority of the problems, you're going to worry about it being somewhere in the middle there where it doesn't really matter. Okay? Simplify it for you. The field is constant and is directed from positive to negative. The edges of the field do bulge slightly since there are no charges outside the plates to balance the horizontal effects of the nearby charge. So there's nothing out here like in here we've got this one and this one that are balancing out, so it's straight down. On the way left over here, there is no force sort of on the left here sort of balancing it out, and that's why you do get that bit of a bulge. But again, we're not going to worry too much about it. We're going to assume, for simplicity's sake, that the field between the plates is constant. Okay? Do you need to write any of that stuff down? I don't think so. At the very least, I might ask you something about a question like this. I might say, explain why this object here goes straight down and doesn't get pushed left or right.
performance.
You could just say, yeah, the horizontal performance cancel, right? You might want to sort of draw that diagram and explain a little bit. That would be the very bare bones least that I would expect it to, sorry, that would be the absolute sort of max, the extent of what I would expect you to get from all that. Not really that big of a deal, really. Okay? Let's go straight to the sample problems, shall we? I'm not even sure why I even bothered with those notes, really. I think next time I'm just going to skip them. Let's go right to the sample problems, which I provided you, did I not? Excellent. Okay, so again, the only thing that really makes these complicated is the crazy numbers and the scientific notation and stuff like that, right? But really, it's just...
If it was just like 3.2 times 1.5, it'd be really easy.
Yeah. All right, so we have a 1.0 times 10 to the minus 4 kilogram charge, and it's 3.2 times 10 to the minus 19 coulombs, and it's dropped into an electric field. The plates are 1.5 centimeters apart. The electric field strength is 1 times 10 to the 15. Determine the net force on the object. Did any alarm bells go off, Peyton, with units in your mind? I.e., are there any units that we need to convert?
Centimeters to meters?
Centimeters to meters. So 1.5 centimeters must equal 0.015 meters, right? I expect you to be able to do that, you guys. I don't know what year they start talking about unit conversions anymore, but I know that you're past it.
So you just move it 2 to the right.
Move it 2 to the left, right? Divide by 100. 100 centimeters in a meter. Divide by 100. Okay, so what do we have? We have mass, we have charge, we have electric field strength. I'm looking for net force. Net force would be, we've got an object like this, we've got electric force up, and we've got weight force down, and one of them is going to have to be stronger than the other, exactly. One's going to be greater than the other. The question is, which one? Well, as always, weight force is a good place to start. Again, please notice that I'm modeling, I'm showing you how to do solutions, and one way to do that, or the best way to do that, is to start with the formula. So we've got 1 times 10 to the minus 4 times minus 9.8. Does the negative matter here?
Yes.
I've got 1 no and about 3 or 4 yeses. It just matters, says Peyton. Gosh darn it. Why does it matter, Hannah?
Because you asked the question.
Just the tone of my voice sort of implies that it's going to matter, right? Yeah. No, I can't. Yeah, it does matter. How come? Because you've got weight force and light force, and they're opposite each other. Just like friction has to be negative so that it opposes the forward force, here the negative has to be negative. Okay? It didn't matter so much when it was balanced because it was always going to add up to be 0, right? But here, there's going to be a positive or a negative, and so yeah, it matters. Does that kind of make sense? Why? Yeah?
Yeah.
Okay.
Before the FW was going to equal that.
It was going to equal it numerically. We knew it was going to be 0 from the question that said suspended, right? Motionless.
So if it's not,
We don't know now.
but if it doesn't say suspended, we just assume it's negative.
It is negative. It is. Not assume. It is, right?
Yeah.
Okay, so that's going to be obviously, maybe not obvious for some of you,
It was
minus 9.8 times 10 to the minus 4. So we have minus 9.8 times 10 to the minus 4 newtons, and that is obviously down.
How come I got 0.00098?
That's the same thing.
So what would we be expected to write?
Either one is fine. Once you get past 3 or 4 zeros, I would expect you to put it in scientific because I don't want to count zeros.
Is it the negative force?
It is not. It is. Excellent.
You're just confused.
Excellent. It is to the negative force.
So it'd be the-
Okay. Thank you,
I
Jason.
put that in.
E equals F over Q. The electric field strength is 1.0 times 10 to the 15.
Positive.
The positive field strength, it would be up, right? Positive. Never had that question before. Charge. 3.2 times 10 to the minus 19. How many ounces is that? 3.2 times 10 to the minus 19.
2.
Excellent.
Didn't mean Zach to come up with it.
Yeah, well done, you guys.
There you go.
3.2 times 10 to the minus 4. Now, the exponents here are both minus 4, right? This exponent, oopsie, this exponent right here is minus 4, this exponent here is minus 4. Is that what you would expect? This is minus 19, this is plus 15. Do you know what the exponent rules are from math? Yeah? You add them together, right? This is minus 4, that's minus 4, the exponents. Is that okay? Is that what you would expect? What does that mean, really? Like, what does it mean?
Same ballpark.
It means they're in the same ballpark. Is that what you said?
Yeah.
Yeah. They're roughly in the same area. Like, you should show concern, alarm bells should go off if this was 9.8 times 10 to the minus 14, and this was 3.2 times 10 to the minus 4. Which one would be bigger? The minus 14 or the minus 4? The minus 4 would be many, many, many thousands and millions of times bigger. In fact, the minus 14 would be what we would call negligible. These two exponents should be either equal or no more than 1 or 2 digits apart. Like if this is minus 4, this should be minus 3 or minus 5. If it's any more than that, one of them is negligible. One of them is so small compared to the other one, it doesn't mean anything. Okay, so they should be relatively equal. Now, when I add them together, what do I get? This one is positive, this one is negative. So what is my net force? My net force is my electric force plus my weight force, which is 3.2 times 10 to the minus 4.
Oh, right.
And I add negative 9.8 times 10 to the minus 4. Could you get an answer that has times 10 to the minus 4 in it? Yes.
What is this formula after you plus that?
What does that formula mean? Peyton's asking about this formula right here, right?
Is it like,
Wait,
why?
I never came up with that. Excellent point. Did I just sort of like, poof, I'm a magician and it came out of thin air? No. I don't do that sort of stuff.
Why? How do you get 9.8 to the times 10 to the negative 4?
That W.
It was this one right here,
Gravity.
right? This one right here, Jason, right?
Oh, okay.
But let's go back to Peyton's question. And it's a good question, Peyton. Where does that formula come from? What is it? Well, what does net force mean? Net force means what's the sum of all the forces? What's the total of all the forces? What are all the forces? Those two. How do you find the sum of them?
Yeah.
You add them together. In fact, F net equals, really, like you can come up with F net equals formulas for just about any situation. You just take all the forces and add them together. That's all it really means, right? So it's not new in that sense, but it's new in that you've never seen it in that particular configuration. Great question. Okay, hey, so is that my answer? Is that what the question asked for? Determine the net force in the object. That wasn't so bad. Is that any different than an applied force, friction force kind of question? Not really, it's just got crazy numbers. Okay. Question number 2. A 4.5 times 10 to the minus 6 kilogram charge of 9.2 times 10 to the minus 15 coulombs is dropped in electric field. The electric field strength is 3.2 times 10 to the 9. Determine the net acceleration of the object, how fast is it traveling after 1.5 seconds, and how far will it have fallen in this time. Before you can find the net acceleration and how far it will have fallen, you're going to have to find the net force. How do we find the net force? Exactly the same way we just did. So, it's going to be 3 steps. You guys go ahead and try to come up with the net force, and then I'll show you the rest.
How much you feel?
Okay, I've got a net force of minus 1.466 times 10 to the minus 5.
No.
Emily's excited because she got that right.
Yeah, that's right.
No, not so much? Oh.
I'm excited.
Joey?
1.4? Just 1.4 times 10 to the negative 5?
Yeah, that'd probably be close enough.
That's exactly what I thought.
Oh,
Oh, I didn't.
isn't that closer than his?
Okay.
If I had more decimals, I just didn't put that.
Oh.
But that's on my part that it shows up as
Yeah.
1.47.
You
As long as I see the work and it's got 1.4
Wait, change
or 1.5, I think I'm pretty happy.
You multiply the loss by? Change the velocity is just VI plus VF, right?
No, VF minus VI.
VF.
Okay, so there's our net force. What did I do? I found the weight force, 4.41 times 10 to the minus 5. That's a minus 4.41. I found the E equals F over Q.
Oh.
Right? I got 2.94 times 10 to the minus 5. And I add them together, making sure that my FW is negative. And I get minus 1.466. At this point here, now I need to find the net acceleration of the object. How do I do that? Now we go way back in time to our old friend, F net is equal to MA. Who needs a review when I do it on a daily basis?
Yes.
What's the mass of this thing?
4.5.
4.5 times 10 to the minus 6. Now, what if the acceleration is down? What kind of number should it be? What did she say? Okay, negative. You're right. That wasn't what I was thinking, but you're absolutely right. Should it be around minus 9.8? Like, what would it be if there was no electric force? Weight force, electric force. If there was no electric force, well, then it would be minus 9.8, wouldn't it? So it should be some number just a little bit less than 9.8. In fact, I get minus 3.26. Well, then it must be right, Peyton.
There's 3.25777777.
Okay, Mr. Milliken.
And I actually did it, so the whole thing using those. Kind of,
Is that the final answer?
kind of.
No, because it says how fast is it traveling after 1.5 seconds, and how far will it have fallen. These, hey, Mr. Bennett, that's review from the first unit.
7.
Why would you do that, Mr. Bennett?
Thanks for the review.
We're gonna have to do it anyway,
Exactly.
and it's easy.
Gosh, Mr. Bennett, you're smart.
I'm already done the question. I'm ahead of you.
Yeah, but he did it.
A equals delta V over delta T.
He dropped that instruction. So.
1.5 seconds.
He probably did.
I get minus 4.89.
4.88666666.
I have 4.9.
I kind of went through the whole thing with all the decimals.
How far will it have fallen? First step, find the average.
Negative 3.665 meters.
Hey, this is a pretty big question, isn't it?
I love this.
I think this one's worth about 10
It
marks.
makes me feel good about myself when I actually.
Yeah? And it should, Steve.
I feel good on the inside.
Does this give you a better understanding of why you need to write the formulas and put them in the correct order?
I know the physics Lord is back.
Oh, I knew it.
Goes back to the.
Oh, not squared.
We want to celebrate.
Is that a 4?
That's minus 2.44 meters per second.
Above that.
Oh, 4.
Kind of
Is
figured.
that
number
the
right
other
here.
one?
Yeah.
The other one is
8, 9.
8, 9. Okay.
Now, last step, Steve. Lord of the physics.
B bar equals D over T
Attaboy. V bar equals D over T.
times the time by the other one, and you got the answer for it.
I'm running out of the paper.
Maybe I should start doing those clocks.
Mr. Bennett, can Steve teach us class next
Yeah, I got it now.
3.9?
Yeah.
7?
I just lost the -5, so it wasn't working.
Well, it was so small that it's basically 0, that's why.
Or you didn't have one of them at -5?
No, I've lost it.
But with
I
F,
have, oh, I already do.
that's F even, right?
Yeah. 3, 9, 5, PE, 5 miles, divided by 3 times 6, PE, 6.
When that happens, you have to like count the decimal points down.
This one's over X.
What's over?
Did you get 3.975 times 10 to the minus 5 newtons for the electric force? Or something close?
Oh, I was pretty sure it was 10 times.
I did.
No, I didn't get that at all. I lost it.
What is over,
I didn't.
when you cross multiplying, what's on the top side of
It
the,
actually doesn't matter. I'll get to that in a second.
I know we had to cross multiply, but I wasn't sure what we're supposed to do. 1.104?
1.1 times 10 to the minus 11 coulombs.
Yes.
And then you go 1 Elch.
Oh, 1 Elch, I think.
1 elementary charge is equal to 1.6 times 10 to the minus 19. So X Elches is 1.1 times 10 to the minus 11. Does it matter whether you put the Elches on the top or the coulombs on the bottom? It does not. Sure, I'll go back and do that in a minute. Where did the what go?
Awful.
Oh, let me finish and then I'll put it up.
Oh, 1 else always equals 10, right?
Yeah.
Yeah.
Yeah, we don't have the right
How do you figure out what, yeah, how do X equals?
So you always just put your Q under your X.
Wait, do we have to look at that 1 L?